Okay, so what does it mean to have a set of vectors that are linearly independent? Okay, so what does it mean to have linear dependency or be independent of one another? So an index set of vectors v1 all the way up to vp in Rn is said to be linearly independent if the vector equation, so x1 v1 plus x2 v2 plus all the way up to xp vp, is equal to 0. Okay, so the sum of the vectors and their scalars is equal to 0. So that means that it has only one solution, and the solution is trivial. Okay, so that's linearly independent. The set v1 all the way up to vp is said to be linearly dependent if there exists weights, so c1 all the way up to cp, that are not equal to 0, such that c1 v1 plus c2 v2 plus all the way up to cp vp is equal to 0. Okay, so they're linearly dependent of each other. So let's think about this as, this is kind of really and truly nothing new that we have done recently. Okay, so if we have free variables, or let's talk about this. So if I have some vector u, let's call vector u, I don't know, 2, 1. How about that? So u is going to be 2, 1. Okay. And vector, let's call vector w, what happened to your glasses? I thought you had glasses the other day. No? Oh, I thought you had them on the other day. No? Did I make that up? That she had something on? You had something on the other day. Well, what was she wearing?
Probably like a hat.
No, she had glasses on her head. You did. Sephora, you wore something. Were they sunglasses? You had something on your face. They were blue. No, they were blue. I promise you had something on. Oh, yeah. Okay. Okay, so let's call W then 4, 2. Okay. So are these linearly dependent or independent of each other? So is there a scalar I can multiply by u to give me w? So there is, yes. So these are considered linearly dependent of each other. Okay. So I could multiply, so this is really nothing new that we've done. So 2u will give me my vector w. Okay. Well, what if I then created some crazy v down here? I don't know. Let's call it, I don't know, 6, 3. I don't know. It's not very good. I'm sorry. So, so let's call this 6, 3. Well, let's call it 6, 2. So what about vector v and vector u? Are these dependent of each other, or are they independent of each other? They're independent of each other because there is not a scalar I can multiply by u to give me v, and vice versa. Okay. So v, and v is linearly independent of both of those two, of u and w. Okay, is independent of both of those. Okay, good deal. Okay, so let's talk about how we can show this. So in example 1, we have 3 vectors, v1, v2, and v3, and I want to determine if the set v1, v2, v3 is linearly independent. So are they linearly independent? of each other. Okay, so what does that mean? What am I going to do? Is this anything new that we've done? Nothing really new. So what could I do here to figure out if they are linearly independent? Okay, so I could put it in an augmented matrix, and the augmented matrix would have, I would need to add a what? 0. Or what else could I do? So either way is fine. Could I leave it as a coefficient matrix?
No.
I could, because it's all zeros over there, so it doesn't matter, right? So I could leave it as a coefficient matrix, or you could change it into your zeros. So it doesn't, like, either way, you could have an augmented or a coefficient, doesn't matter. Either one. Okay, so we still want to reduce it down. So take a second and reduce it down and see what happens here. And Sephora, the color is probably not very good for you to see. Would you like me? I'll change it to black here. Well, it's hard to see sometimes colors up there.
What is 1 minus 4?
Did I get that down right? Dylan? Did I do that right? Did I get it right? Okay. It's Monday. Brain. Okay. So could we stop right here? Just to answer question A, part A. Could I stop here? Okay. So I can stop here because I see that I have a pivot. 1. I have a pivot. 1. But what do I have in that last row? 0. So what does that mean? So let's take this in terms of, so I've got x1, this is my x2, and this is my x3. So what do I have as x3? X3 is what? So what is x3? Is free, yes. Okay. So x3 is free, yeah. So that's important. All right. So since I have a x3 is free, then these are linearly what? Independent or dependent?
Okay, hold on. I'm just lost. I don't.
Oh, Dylan said I was right. So, but oh, you do?
I just don't know. What operation? Yeah, my bad. But what operation is it?
Am I good? Okay. So if the first question was determine if it was linearly independent, we could stop there and say that they are dependent. But it also says, if possible, find a linear dependence relation among B1, B2, and B3. So what is it asking for? The coefficients. So some form of scalars, right? So what could I do? How would I now put my solutions? Could I keep going? Could I keep going to reduce here down? Just maybe one more step. Let's one more step down. And what could I do to row 2? So that would be, I can multiply by 4 and subtract. So that would be what? 1, 0, negative 2. 0, 1, 1, 0, 0, 0. Okay. So what do my solutions look like? So x3 is what? It's free. So x3 is free, right? So what does this look like? So I put it as a coefficient matrix, right? So let's think about this. This is x1 minus a 2x3 is equal to what? 0. I left that out, right? So remember I left that out. So just make sure that you're not saying that x1 is equal to -2, right? So we left it as a coefficient matrix. All right. And then the next one represents that x2 plus x3 is equal to a 0. And then the last one is that x3 is free. Do y'all agree with that? Okay. So as your solutions, what would it look like? So x1 would be a, what, 2x3? X2 would be a negative x3, and then x3 is, of course, free down here. So it's asking for a relation, yes? So it's asking for a relation among these vectors v1, v2, and v3. So it actually wants you to plug in. So if x3 is free, what does that mean I can do for x3? I can choose anything, right? I can choose whatever I wanted to. So all of your solutions could be different. Okay, so if you chose x3 to be 10, it would look different if you chose x3 to be equal to a 6. Yes, so what you get as this following thing as a form of vectors could be different. So I'm going to choose x3 to be 2. So if I let x3 be 2, then x1 is going to be what? 4, and x2 is going to be a what? -2. So my combination here, so my dependence of my relationship here, so it'll be 4 v1 minus 2 v2 plus 2 v3. Do y'all agree with that? Plus 2 v3. And then that's all going to be equal to a 0. But this is one out of infinitely many possible solutions, right? So yours, like I said, yours could be different. This part doesn't, since it's, they are dependent upon each other, this is created just because I chose x3 to be 2. It should just be -5. You get a whole difference. Yes? That makes sense? All right, so y'all take number 2 and try to work number 2 for me. Okay, so if I set my matrix up here, you can use, I don't know why I put a negative there, you can use this as coefficient matrix or leave it as an augmented matrix. So let's change it and let's make it augmented. Okay. So what's my first step in doing my reduced echelon form? Here, I have a 0 at the top. So what do you think I need to do? Interchange, yes. Okay, so we could take row 2 and that becomes my row 1. Are y'all okay with that? Or is that what y'all did? So before I get started, all right, then multiply 5 times row 1. What's that? Oh, goodness. I don't know why this keeps doing this. All right, so that's what? 0, 5, 10. -2. 5. Why is this? Is it -5? I multiply by negative. So let's do that. All right, and then positive 13. Man, brain. Yeah. Okay, so is this going to be linearly independent or is this linearly dependent? Independent, there are no free variables, yes? So no free variables. So AX equals 0 is only going to have trivial solutions. So it's linearly independent. Okay, good deal. All right, so we've got some special ways to determine independencies here. So if we have one vector, okay, so if we're looking at just at one vector, we can determine the linear independency if and only if one of the vectors or the v does not equal to 0. So if and only if v does not equal to 0, then linear independence. Linearly, I can never spell that word in my head. Linearly independent. I don't know what's up with this. So there is only one solution, right? So there's only one solution. All right, so if you've got two or more vectors, so you can determine by multiples or by theorem 8 in your book. Okay, so by multiples, we already kind of talked about this. So if we've got one vector x, what did I think we said 4, negative 2, and we have vector w to be 8, negative 4, and we have vector z to be 8, positive 4. Then the set x, so the set xw are what? So they're linearly dependent of each other because what? They're multiples, yes? So they're dependent of each other because 2x gives you your w, yes? All right, what about x and z? Independent, okay, so there's nothing that we can multiply together, so they are independent. Okay. All right, and then we can talk about by using, if we've got more vectors, so if there's like 3 or more vectors in our set, so we can use, this is theorem 8 out of your book in this section. So if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. Okay, so what does that mean? So if we have some matrix A with V1, V2, all the way up to VP, then A represents a matrix that's n by P. Yes, so it's n by P. Okay, so A, oops, y'all, this pen just keeps going out. I don't know what's happening here. So AX, so then AX equals 0 corresponds to n equations with P unknowns. Okay. And since then P is greater than N, right? So P is going to be greater than my N. We have a non-trivial solution, so it is dependent. All right, so let's take a look at what I mean by ways to determine just taking our vectors and determining linear dependency. So let's look at example 3 here. So are the following vectors dependent or independent of each other? So the first one is the set UV. So take a second and determine if UV is going to be linearly dependent or independent. Okay, so A part is a little more simple than especially B part. So let's look at A first. So are those sets, so is UV, is that independent or is that dependent? So we can just go by our multiples. So is there something that I can multiply by U to give me V? No. So this set is going to be what? Independent. So yes, we'll say yes. Lord to be. And then it won't let me use my finger to write on this thing. Okay, I give up. So UV are going to be linearly independent. All right, let's look at C. Let's skip down to C. So what do I have going on here with the set here? I have UV, W, Z. So if I set this up in a matrix, what do I have?
You have a set that contains more vectors than there are entries in each vector.
Okay, so that means that they are going to be what? Dependent of each other, yes? So C is going to be dependent. I'm sorry, I can't write on my screen. Oh, there we go. And of course, I write a circle. So, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yep. So, P is greater than my N, so we're linearly dependent. Okay. All right, let's look at B. So let's get back to B. Yes? So this one is one we just can't tell by either of the two ways. So we've got the same amount of columns and entries here. So what could I do to set this up and to see? There we go. I can simplify this down. So I'm going to have what? 1, 2, -4. V, which is -6, 2, 3. And then W, which is 0, -4, 0. Okay. So if I reduce this down, what do I get here? 1, 0, 0, -6, 0. What's that, 14? -4. 0. Is that right? I was trying to go from that second row to reduce the third row. To have something in that third spot. Does that make sense? So to get something in that third area.
Yeah, I did 4 times the first row, plus
Yeah, which is, I think, what we'll get no matter what here. So then if I take half of this is what, 7, -2. And then if you take that row, let's go ahead and take that row and do this. So that's what, 1, 0, 6. So either way, you should have gotten something to maybe this point. Okay, so now what does this now mean that we've reduced it down? And we can stop here. We do not have to, as long as we get it in echelon form, we can tell that what happens. I have no what? No free variables. So since there's no free variables, then what? It's linearly independent. Okay. Good deal? And then this one was linearly independent as well. I didn't write it because my thing wouldn't work. Okay. All right, so now, I can't believe I'm going to let y'all go early again.